Cool. Good afternoon, everyone. My name is Adrian Woodhead. This is my colleague, Elliot West. We're both developers at hotels.com, which is part of the Expedia group. And we're here today to talk to you about tools and approaches for migrating big data sets to the cloud. And this is based on our real-world experiences about 2 years into a big cloud migration project. So just quickly, the agenda for today's talk, so you know what you're letting yourselves in for. We're going to talk a little bit about our cloud migration plan, why we wanted to migrate our data processing to the cloud, and how we came up with a plan for doing this. We're then going to talk about one of the first issues we faced, which was around replicating large data sets into the cloud, and a tool we developed called Circus Train to do this, which is open sourced. We're then going to talk about some of the surprises we ran into once we were running in the cloud on a big scale. A lot of it is around cross-account data sharing. We're then going to talk about another tool we developed in open source called Waggle Dance, which allows you to federate queries across Hive metastores. And then we're going to end up with something called apiary, which is our data sharing pattern and a way of building like a deployable unit that improves access to data in the cloud. So firstly, a little bit of information about the Expedia group. So I know this looks like a marketing slide, but it's not. So before the developers run screaming for the doors, I'll explain why we've got this up there. So Expedia consists of a number of different brands, companies they've bought over time, things that have grown out of it. And what's interesting about this is we have some data sets that we want to share across the entire company, so all these different groups. But then we also have parts of the company that have their own use cases, their own data sets they don't necessarily want to share. And different parts of the company move at different speeds and are also more or less technically advanced depending on what they're doing. So that's kind of one thing that's a bit interesting to know about us, and it also affected how and what we ended up building. So some of these groups have been going for like 20, 25 years, so we've got a huge amount of physical infrastructure on the technology side, which predates the cloud even having existed. So we've obviously got this big amount of compute that if we're going to move to the cloud needs to be migrated in some way. So why are we even thinking of doing this? So the three main reasons for us, I'm just going to quickly cover them. The first one that I'm sure all of you have heard a lot about is cost savings. So running all of that physical infrastructure ourselves, upgrading it, maintaining it, having our own operations people, our own data centers costs us a lot of money. And if you use a cloud provider like Google, Amazon, or Microsoft, they can do it at a much bigger scale, and everyone below them saves. So that's kind of interesting, but as developers, much more interesting for us is being able to get our hands on new technology quicker. And the reason this is an issue for us comes back to kind of how our company is structured. So on-premise today, we have one very large shared Hadoop cluster for the entire company. So this makes things easy operationally, but what we found is we have certain groups, like hotels.com that we work for, who really want to use the latest features in the Hadoop ecosystem. So we're always pushing for upgrades, like upgrade, upgrade, upgrade. And then we have other parts of the company who are a bit slower, or a bit more conservative, and they're a bit more like, please don't touch anything, it works, don't upgrade anything ever. So our poor operations teams are kind of being torn between these two extremes. And then what that means is whenever we want to upgrade our on-premise cluster, is we have to convince the entire company, and then everyone has to go at once. So what this has meant in practice is upgrades have been few and far between. So we end up not having access to all of this new technology, and that impacts certain parts of the business. The other thing that's really interesting about the cloud for us, again, with this shared cluster, is there are certain times when there's a lot of contention for resources. Lots of people are running queries, lots of ETL jobs are running, and then we'd really like to just be able to spin up 100,000 more nodes and have things go quicker. It's obviously hard to do when you've got a physical data center and you need people to rack and stack machines. And this is one of the big obvious benefits of the cloud, that you can just quickly spin up more resources when you need them. So what that means for us on the sort of data warehousing, data processing side, what we looked at, what we needed to migrate is we have a data warehouse that weighs in at about 2 petabytes. We have thousands of data processing jobs which are connected in all kinds of weird and wonderful ways to produce these data sets, hundreds of data sets. For the purpose of this talk, we're just going to be focusing on the data sets we have stored in HDFS with metadata, accompanying metadata stored in a Hive metastore, which is a fairly common pattern. The data on HDFS is in many different file formats, ORC, CSV, Avro, basically any file format that Hadoop supports, we've probably got it. Similarly, when it comes to the tooling to access this data, we've got Hive, we've got MapReduce, we've got TES, we've got cascading, all kinds of tools that plug in via the JDBC connectors. And we also have a wide variety of users accessing the data. So we've got analysts, we've got data engineers, ETL jobs, data scientists. So as nice as it would be to migrate this by just stopping the world and migrating it to the cloud and then turning on again, this is just not practically feasible at this scale. So when we were tasked with this, we had a look at a very high level. Simplistically, on-premise today, we have a number of jobs that produce data sets that are consumed by users. So we looked at migrating the jobs to the cloud first, but as I mentioned, they're kind of tangled in so many ways. Untangling all of that's going to take a lot of time. So we decided instead to focus on the users. So some of the earliest champions for our cloud migration were our data scientists who wanted to be able to get their hands on all the new data science tools that are being evolved very rapidly. So we figured if we moved them to the cloud first, they could start unlocking some business value very, very early on without having to wait for a bunch of jobs to be migrated. So obviously having users in the cloud without any data isn't much use. So the simplest way to get the data to them was to find some way of replicating the data into the cloud. So we'd have the data on-premise and in the cloud, and users would be able to move over to the cloud. The other benefit of this approach is that our data engineering teams could now spend a lot more time on figuring out the best way of migrating those jobs to the cloud. So they wouldn't have to do like a really massively rushed lift and shift operation. So we hope that would lead to a better quality of migration of the jobs. So then at some point in time, obviously, we hope to have migrated the jobs and the data sets, and then everyone would be happy in the brave new world in the cloud. So what this meant is that we were going to have a period of years where this migration was going to be taking place to untangle all of this. It also, whilst this is happening, all those data sets are going to be changing just like they do today. There's going to be data coming in incrementally. These data sets get updated hourly, daily, whatever. So we need some way of being able to continuously replicate this data over. So we have the data available on-premise and in the cloud. So our data set replication problem then, what we need to solve on a technical level is we need to get the data off HDFS into our cloud data provider. So we've chosen to go with Amazon, but most of the concepts I'm talking about here will apply equally well to Google or Azure. So some way to get the data across, and then obviously we need the metadata, which has information about that data that needs to go across too. So in our case, from an on-premise Hive metastore to a Hive metastore in Amazon running on EMR. And then one of the very important things for us is we want to make sure that the data in the cloud is available in a coordinated manner. So by this, what I mean by this is we only want people accessing the data when it's all there. Like, we don't want them to be able to have partial reads accessing the data whilst it's being replicated. So the data gets replicated first, and then only does the metastore get updated with the locations of that data. So then what we're guaranteeing by doing that is that our users have a consistent view of the data. So they might get data a little bit late in the cloud, but they'll have the correct data. So these basically boil down to our requirements for a data replication solution. So kind of in the time-honored fashion of developers everywhere, we thought we could just find a nice open source solution that would do this for us. We also work for a company that's happy to pay for good proprietary tooling, so we looked at a number of those. So what we were really surprised about, so this is about 2 years ago, is that a lot of the replication solutions out there either didn't replicate the metadata at all, or they did it in a very naive fashion where you could get partial reads of the data whilst the replication was taking place. So nothing really ticked our data consistency box. We had a number of other issues, which was kind of a bit more unique to our setup at the time. So we were running an older version of Hive on-premise, and we were blocked from upgrading that. So there's some features in Hive, newer features in Hive, which allow you to do data replication, but we didn't have access to any of those. Our team also doesn't have root access on Hive metastore, so we couldn't add our own Hive metastore hooks. So we needed a replication solution that could live outside of Hive and not require admin access. So nothing at the time out there that we looked at met all of these criteria. So we reluctantly moved on to creating our own tool. So the first and always most difficult thing in coming up with a new tool is the name for it. So we came up with the name Circus Train, and the reason here is we've got the whole Hadoop, elephants, and big top theme. And we also figured we were taking like a crazy data circus from one place and moving it to another place. So what Circus Train does is it first looks in the metastore on premise to find out what needs to be replicated and where the data is located on HDFS. It then spins up a distributed copy mechanism to actually copy the data over to the cloud storage system. And on each run, it replicates the data into a uniquely named Snapshot folder, which I'll talk about in a bit more detail later. Once the data has been replicated successfully, it then updates the replica metastore with the metadata, and the only thing it transforms by default is the data location, so it points them to S3 instead of HDFS. And then when that completes, it sends notifications. By default, we send notifications using Amazon's simple notification service. What this looks like, just to make it a little bit more concrete, this is what a Circus Train configuration file looks like. This is in YAML, but you can use different configuration mechanisms. So the first thing we're doing there is we're providing the thrift service endpoint URLs of the source and the replica, so Circus Train knows where to read the metadata from and replicate it to. Here we're just specifying a single table replication from a database named ETL, a table called clickstream. And we're also, in this case, providing a partition filter to limit the amount of data that gets replicated on each run. So here we're just saying replicate the last day's worth of data based on the partition column in the source dataset. So this would be really good if you're replicating a dataset that only changed once a day, but you can customize this in various different ways. We then need to give it the location of the data in the replica file system, so it knows where to repoint all the data locations to. And finally, we're configuring the SNS listener at the end. So we typically use like a bash script. We run the Circus Train executable, give it the location of this config file, and we set this up in a scheduler like cron, Azkaban, or Airflow, number of different replications, different times of the day, and off it goes. You could also trigger Circus Train to run when your source data set is finished rendering. Lots of different ways you could do that. So I'll do a little bit of a deep dive into a couple of the more interesting features that we find very, very useful. So I mentioned we have this distributed copying mechanism, and we support a number of different source and target file systems. So out of the box, we provide support for Hadoop's distcp mechanism, which I'm sure many of you have heard of. So that's really useful if you're replicating to HDFS. We also provide our own implementation of a copier, distributed copier, that copies from a Hadoop file system to S3, and that uses Amazon's S3 APIs to do the copying. We've got support for Google's cloud storage system in sort of the way I've shown you here on the table. And those copiers, they all require a cluster to run. So they spin up a cluster, and that does the distributed copy. And Circus Train, we find it's useful to run it in different ways. So sometimes we run it on-premise, and we push the data out to the cloud. You can also run it in the cloud and pull the data in. And which one you choose really depends on your networking configuration, bandwidth, where you can more easily get resources, which of those clusters is going to be cheaper to run, etc. What we also found after we'd been running in the cloud for a while is we wanted to be able to do replications between regions in Amazon. So we wrote an S3 to S3 copier, which not only uses Amazon's S3 API, it also uses Amazon's infrastructure to do the copying. So you don't even need a cluster at all to do that kind of copy. So that's quite useful. We've written these copiers in such a way that you could plug in your own. So if you had some exotic file system that you wanted to support, you could configure Circus Train to use that. And we kind of ate our own dog food. So we released something about a couple of weeks ago where we use this mechanism to write our own plugin, and that copies data out of Google's BigQuery into S3 and Hive. I touched on it a little bit earlier on. So a lot of these data sets are really, really big, and you don't want to replicate the entire data set every time you run. So we have this concept of partition filters, and we use Spring's expression language in the configuration files to do that. So this is just doing the last day, like I showed you earlier, but you could come up with much more sophisticated ways of being able to identify the data that's changed in between each run, and it'll only replicate that data. What we found when we were running in practice is we had a few data sets that were really, really big, terabytes in size, and the way they changed in between replication runs isn't something that you could capture by a partition filter expression. So we added a feature which we call a Hive diff, and what that does is it looks at the metadata on both sides, and then it actually looks at the files on both sides, and then it figures out what's changed between the last time it ran and now, and then it'll only replicate that data and metadata. So this was one of the core features that we were really looking for in other replication systems that were lacking. So I'll just talk about this in a little bit more depth. So here, if you can imagine, we're replicating an entire table from on-premise to the cloud. What I'm describing here applies equally well to partitions within a partition table. So the first time you run, it will replicate this entire table, in this case, to a uniquely named snapshot folder. We're just calling it snapshot 1 for simplicity's sake. The actual folder names are a bit different in reality. So when you run a replication, it'll replicate it there. When you then replicate that table again, it'll then replicate it into a folder called snapshot 2. So then if you can imagine, after you've done this, a bunch of ETL jobs come along, people start running queries, they'll access the metastore, they'll be directed to use the data from that location, and jobs start reading data from that location. So whilst this is happening, you then run a third replication. So what we do then is, whilst those jobs are running, we don't touch that data in any way, we replicate into a third folder called snapshot 3. So the jobs aren't impacted in any way. So then what happens is time passes, as new jobs and queries come along, they talk to the metastore, they now get snapshot 3 as the location to read the data from, and after a certain amount of time's gone past, nothing is accessing snapshot 2 data anymore, and nothing ever actually read from snapshot 1 in this example. So Circus Train has this concept of housekeeping, where it keeps track of all of these locations, and after a configurable amount of time, it will then recognize that this data is orphaned, and it'll actually delete it off the replica file system. So very, very briefly, some of the other features that we've developed over time, we've tried to make things as pluggable as possible. So the notifications that I mentioned there, you can write your own notification mechanism if you don't want to use SNS. We gather a lot of metrics whilst we're running. By default, we report that to Graphite, but you could write your own metrics gatherer if you wanted to. We've got a number of different copying modes, so you don't have to copy data and metadata. You can copy just the metadata or mirror it if you want. We support replications of Hive views as well as tables. You can plug in your own transform, so if you want to transform the metadata in some way, like we've changed one of the SERDs we use to be a different one in the cloud to what's on-premise, you could plug that in. We have support for SSH tunneling between the metastores, so if you've got firewalls and all kinds of other stuff, you can often use that as a way of being able to bypass them. We store the credentials in Java key stores, and we don't put any of that stuff into log files, which some of the other copiers do. And there are a bunch of other features, but I don't really have time to go into all of them. So if we look at where we are now with our data replication via Circus Train, we have all our end-user data sets are being constantly replicated to the cloud. So we've got about 100 or 200 of them just within hotels.com. It's been running in production for over 2 years, and in that amount of time, we've replicated well over a petabyte of data without any issues that I'm aware of. It's being widely used across different parts of Expedia, and we've made really good progress in migrating a lot of our analysts and data scientists over to the cloud, and they now have a bunch of tooling that they would never have had available to them in our on-premises world. And our engineering teams can now spend a bit more time figuring out how to migrate their jobs over, and we've open sourced it, so that's great. So if you're thinking about the bigger cloud migration journey, you might think, job done, we can all go home now, fantastic. But what we discovered, kind of what happened next, is this wasn't the case. So I'm going to hand over to Elliot now. He's going to tell you what happened after we'd replicated the data.
Thanks. So moving to the cloud gave us new abilities to innovate, but it also became a rich new source of problems. And the first major problem we encountered next, I'll describe now. So our data science team were our earliest adopters of the cloud, and they couldn't actually wait for us to do a wholesale migration of our data platform. So they went on ahead to AWS, they set up their own account, they spun up their own infrastructure, their own Hadoop cluster and Hive cluster, and this gave them a great head start. Later on, we came along, we set up our main data platform account, and then we too set up our own cluster, our own Hive instance, and we started replicating in those core data sets from our on-premises cluster using Circus Train. So, of course, the data scientists were then really keen to get access to those core data sets. But it's at this point we kind of realized what some of the benefits of being on-premises that we kind of missed. And that was that when you have one large shared cluster for your whole organization, it makes some things really easy. So you have all of your data in one place. And if anyone in your organization wants to share a data set or explore data sets and discover new data, when you've got it in one place, discovery is just like browsing one metadata catalog. And sharing data sets is simple as just providing a fully qualified table name to whoever wants to consume it. But in this new sort of cloud architecture that we had, this just wasn't possible, because it seems that Hive seems to have been built around this premise that it's going to run on one large cluster. And so it provides no means to bridge across multiple clusters and indeed multiple accounts. So when we looked at this problem more, we saw that we were actually going to have more across cluster dataset dependencies. So we, Hotels.com, are consumers of Expedia data. And they actually, at some point, they went and set up their own AWS account and spun up their own cluster, and that's where those data sets live. And then when we started to look at the roadmaps of other brands, we saw that they were going to create their own accounts and clusters, and sometimes more than one as well. And so what we were effectively doing by using this architecture was creating a bunch of data silos. And this was really going to inhibit our ability to realize the maximum value of our data. We weren't going to be able to collaborate like this. So how could we solve this problem? So as we described, when we were on premises on that one large cluster, it seemed to work really well. So maybe we could go back to a model like that. Maybe we could get all of those accounts, take all the people in it, and all the infrastructure, and then just dump them into one large account for the whole organization. We'd set up a large cluster for everyone, and we could put the data in there. This just wasn't going to happen. So it turns out that there are actually good reasons for having multiple accounts. So firstly, the owner of account can set it up to meet their use cases. It also provides a good means to limit the blast radius of any event that you might have in an account, such as an intrusion. So this unification was never going to happen. So Adrian talked about replication. We have a tool that's we're quite comfortable using to replicate data sets. Maybe we could replicate the data between accounts. So this is technically possible, but there are some big drawbacks to this. So the first drawback really is you're going to be creating multiple copies of this data, and that's going to incur increased storage costs. It's also kind of quite unnecessary, because reading data across account on S3 in the same region is actually pretty easy to set up. So it's a bit unfortunate to do that. The other thing is we'd have to set up and manage and monitor all of these replication jobs that's moving the data between these accounts. So we didn't really want to do this either. So what we really wanted was this. We wanted autonomy in our own accounts. We wanted our own independent infrastructure. But we wanted the means to be able to collaborate with one another. So we kind of needed some kind of federation at the dataset level. So what we did is we built a thing called Waggle Dance. And I'll describe how it works with the example we were talking about earlier. So here we have the data science account, and there they've got their own workload running on a cluster. They've got a metastore that stores metadata about their data sets. And they have some S3 buckets in their account where they're writing the underlying data for those tables. Similarly, we've got the same in the main account, a similar setup. And this is all running in one region, US West 2. So what that workload then wants to do in that data science account is it needs to be able to get a data set from both its own local account and also the main account. Now, technically, what it needs to do is read data from the S3 buckets that belong to the main account and also the data science account. Now, as I said, this is actually really easy to set up with the appropriate S3 policies. But what you can't do is talk to multiple metastores concurrently. And this is true not only of Hive, but also other data processing frameworks that integrate with the Hive metastore. So what Waggle Dance does then is it sits in the middle, and it's a request routing Hive metastore proxy. So it presents exactly the same Hive Thrift Metastore API to that workload. As far as that workload is concerned, it's talking to a regular metastore. So that workload, and that could be an ETL job, a machine learning job, or an analytics tool, that's going to make metadata requests to Waggle Dance. Waggle Dance is going to inspect those, look at the databases to which those requests refer, and then it's going to figure out which metastore it needs to route them to. It's then going to gather back the responses from the various metastores and pass that back to the workload. Now, those responses are going to include location information about where the underlying data lives, or which S3 paths. And so it's then going to use those to read that data. So what does this look like from a user perspective? Well, let's first consider the siloed view. So I'm a user. I want to see what databases are available to me. Without any federation, in the main account, I might see an ETL database, which contains the tables that are generated by our ETL processes. And then in the data science account, we might have a machine learning database that contains the output of our machine learning jobs. And then if we go down a level, inside those databases, we'll have the datasets themselves. So here in the main account, I've got a core dataset, hotel, and that has like records for all of the hotels that we advertise on our website. So for simplicity's sake, let's just say it's an ID of a hotel and the name as a string. And notice that the underlying data for that table is stored in this HCOM main bucket, and that bucket belongs to the main account. Now, similarly, in the data science account, we might have a machine learning job that works out what's the best image to display for a given hotel. So we call that the hero image. So that might have the hotel ID and also a file name field for the name of the image. And notice here that this data for this table is stored in a different bucket, the HCOM data site bucket, and that's owned by the data science account. So these two tables then, they're in different clusters, in different accounts, and owned by different people. But they are related. There's that foreign key there. They both refer to the same hotels. So it's not inconceivable that someone will want to join these things together. So how could someone do that with Waggle Dance? Well, it's quite simple. So in that data science account then, in my workload, in the Hive client, what I need to do is I need to point it to the Waggle Dance instance instead of its local metastore. And you can do that just by, no cone changes are needed. You just need to use this property here, Hive metastore URIs, and you need to set that to the endpoint address of the Waggle Dance service. Now, once you've done that, when you go to see what databases are available to you, you get this combined view. So we've got the ETL database from the main account and the machine learning database from the data science account. And then you can do something a bit more complex. So here I'm joining those two tables, and I'm just pulling out the name of the hotel and the hero image for a given hotel. And this is a mock-up, but in practice, it honestly does work. So here you get this result, which is combining that data from those different accounts. Yep.
Would that work across Amazon regions? Because in the bucket name, you have no region at Copiers, right?
Yep, we can get to regions, yep. So in this example, this just deals with 2 metastores, but we can actually federate across multiple metastores as well. Okay, so our cloud journey to this point then, we have our data scientists, our data engineers, and our analysts working productively in the cloud with our core data sets. We've given them methods for migrating their own data sets off of our on-premises cluster using Circus Train. And we've also given them back that ability to discover, explore, and share data sets in the cloud, just like they had on-premises. But along the way, we've accumulated a number of problems. So the first thing to note really is that the adoption that we had of these tools was far beyond what we expected. And so we've ended up with this sort of ad hoc deployments all over the place. So we don't have a great view on what's going on. So we're not exactly sure which data sets are being replicated to where, by whom, which metastores are federated, which tools are talking directly to a metastore and which are going via a Waggle Dance instance. And it's all quite operationally complex as well. So there's a lot of networking that needs to be sorted out so all these things can talk to each other. And also there's a lot of security configuration as well around those S3 bucket policies. So kind of unexpectedly, what happened next is multiple architecture teams within our organization started to come up with structured patterns for deploying these services. And what I found quite interesting is they all pretty much came up with the same thing independently. And the pattern we call apiary, and it looks like this. So this gray box here, the intention is that this would be deployed in each region, in each data account. So the first thing to note is this, in this pattern, is that we have an instance of Circus Train in there. And that's there both to migrate datasets off of our on-premise cluster, but also to provide some cross-region replication as well. The next thing to call out is this read-write metastore service. So this is there to maintain metadata about the datasets that are owned by this account, that are produced and managed by these local workloads. Now, this metastore service is backed by a relational database, and that's a standard Hive thing. But it's important because we use that database in conjunction with another instance of this metastore service. But this time, it's a read-only service. And we provide that, we expose that to the other account. So we don't mind sharing some of our data sets with accounts outside of our own, but we don't want them to be able to do things like drop tables or inadvertently add partitions to our data sets. So that's why that's read-only, and that's why that's there. Now, local workloads, they don't talk to the metastore service directly. They go via a Waggle Dance instance. And that's there so that we can provide them access to data sets throughout the organization. So when you apply this pattern, it looks a bit like this. So here I've got some example accounts going horizontally, and we've deployed in 2 regions, US West 2 and US East 1. So this diagram is meant to illustrate the 2 fundamental objectives of this pattern. So the first objective is to reduce storage costs. And we do that by saying that if you're in one account in the same region and you want to access a data set in our account, you do that via federation. And what that means is ultimately you'll always be reading the master data set from S3. What we don't want users to do is replicate and create their own instance of the data set in their own account, because that's just a waste and costs us more money. The next objective of this pattern is to reduce data transfer costs. So imagine I'm a user in a different region, and I want to access one of your data sets. Then we don't really want them to federate across region. Because what that means is every time they run a query or a workload, they're going to have to pull that data set across from one region to another, and we're going to incur cross-region data transfer costs. So in that case, what we'd do is we'd replicate that data set for them into the region of their choice. And then once it's there, then they're free to federate again, but in that other region. So what I really like about this pattern is it's changed the way that we think about our tools and our architecture. So initially, Circus Train and Waggle Dance were meant to be temporary tools, temporary workarounds to these inconvenient structures that had appeared in our cloud architecture. But once we accepted that this was our architecture and this was the way we were going, and we became comfortable using these tools, then we could think more optimistically and think of the opportunities that they gave us. So all of this replication of data from on-premises, at first, it's hundreds of big data sets. It's got quite a lot of operational overhead to do this replication. But once we were good at doing that, then we could think of using these tools instead, Circus Train, to provide cross-region replication. And that would both give us a backup and also give us some way to deal with a region failure should that occur. The next thing is those segmented accounts. When we first saw that, that was inconvenient. They're potentially going to limit the value we could extract from our data. But once we could deal with that, then accounts became a useful architectural primitive. So now if we needed to create a new account, we could do so without worrying about the impact on our data platform. Okay, so if you're thinking about building a data platform like this, it's worth remembering that our problems might not be yours. So we had to deal with a lot of organic architectural growth in the cloud. We had a lot of legacy in terms of the number of file formats and partition layouts and all those sorts of things that we had to work with. And we also had a huge tool set with which we had to maintain compatibility. But if you don't have all of these constraints, then simpler things can work really well. So we've seen people migrate data sets from on-premises to the cloud using a simple create table, a Hive create table as select command. And also, if you don't need multiple metastores and you're quite okay just having one large metastore, then you should probably do that because it's going to make your data sharing and discovery piece quite a lot easier to do. Okay, so both the tools we talked about today have been open sourced, and they're available on the hotels.com GitHub account. We hope there's some good documentation there. We think it's good. But if you do check them out, then we'd really appreciate your feedback, and we'd love to see issues and pull requests, if you have them. So we have some stickers at the front and back, and we have a bit of time to take questions.
So my question is about Circus Train. I see some kind of overlap between Circus Train and overflow. Somehow, if we start this project today, we could implement Circus Train like a Python library that we point to the metastore and create these pipelines automatically. So would you implement Circus Train as an independent project, or would you consider using something like Airflow?
Okay, so the question, we just need to repeat them because this gets recorded. There's also a mic there if anyone wants to use it. So the question is, using something like Airflow, which has got various sort of plugins written in Python that you can use to do various things, and it sounds like you're saying there might actually be an Airflow plugin which does data replication. So when we built all of this, Airflow this was 2 years ago, so I wasn't aware of anything out there at the time that could do it. I would also wonder whether that does the whole, first the data, then the metadata, and whether it supports the idea of these snapshotted locations, because it might not. Like, a lot of these solutions look really good, and if you're just migrating data and you don't care about people accessing it at the same time whilst it's in flight, something like that might work really, really well. You just do a one-shot migration and you're done. We, unfortunately, didn't have that luxury. We knew people were going to be accessing the data all the time for years, so we had to go for something like this. But like as Elliot said, our problems may not be yours, so something like that might actually work very well for you. Yep. Yeah.
How do you run the metastore? So do you have a cluster of machines that you keep up to run the metastore? Because it's a brittle piece of technology to keep alive for such scale. So I wonder, what's the operation look like?
Yeah, so we run it with...
Repeat the question.
Sorry?
Repeat the question.
Oh, so the question was, sorry, how do we run those metastores? So we run them in a high availability configuration. We deploy them in multiple availability zones. And
there's
then
a load balancer in front of them.
Yeah, there's a load balancer in front of them, and also we have a high availability arrangement as well on that database that backs those metastore services.
Standalone, there's no Hadoop cluster.
No.
That's correct. Yeah.
So just a question. So you talk about Waggle Dance, and you talk about basically different type of databases across different accounts. How would that work if you want to do the same kind of database but in lower environments? So for example, shareholders are aware of paying and copying data into lower environments, you can develop them in a lab environment. If you've got an accessibility to your prod data through this, and you want to be able to say, I don't want to copy data down to my test, I just use Waggle Dance, point to that prod data and pull that down. Is that possible?
I'll take that.
So the question was, I think, was can you use Waggle Dance to go across different environments?
Yes, basically like, so I want to run my kind of code, but I don't want to copy production data to lower environment. I could just point it with Waggle Dance.
Okay, so you might have a job running in your staging environment, and you want to consume production data. So yeah, if the network connectivity and the S3 policies allowed it, then there's no reason why you couldn't do that.
How would the databases work then? Is it both the same?
Oh, so they've both got the same name. Yeah, so that is a problem. So we have a couple of strategies in Waggle Dance for dealing with overloaded database names. So one of those strategies is to apply a prefix. So each metastore instance every database in that metastore will have a prefix applied to it, so that they'll all end up being uniquely named. Another thing you can do with Waggle Dance is you can curate the list of databases that are exposed at the federated endpoint. So you might not necessarily see everything. So then you can be a bit more selective about which databases you see. It doesn't support sort of remapping of names. So I think that still might be an issue. You'd have to use the prefixing. Yep.
Yes, have you had any like acquired subsidiaries that are using GCP or Azure and had to deal with them that want to keep their data where it is?
Yeah, so the question is, have we got parts of Expedia that are using something like Azure or GCP and they want to keep the data there? So yeah, we have a lot of search engine marketing data going through Google, DoubleClick, etc. And all of that's in BigQuery. And that is definitely a problem, because if we want the whole organization to get to that data, we then would have to set up basically this entire parallel security, access, everything in Google as well as what we're doing in Amazon. So what we've decided now, the policy now, is those data sets, if there's specific small groups of users who already have access set up in Google, they're free to use that. But if any of that data needs to be joined against any of the source data sets back in the mothership, that's basically that Google BigQuery connector we wrote. That's exactly to deal with that. It pulls the data back into Amazon, and that's where the action happens for now. So I see the door's been opened, which I think is our hint that we're done. We'll be available either outside or downstairs afterwards if anyone wants to ask more questions. Grab stickers, and thank you very much.